We're going to see satellite communications in this unit. Satellites are useful to connect remote areas, or when you want to broadcast video or data to a vast amount of territory with minimum infrastructure. A communication satellite is an artificial satellite that relays and amplifies radio telecommunication signals between a source and a receiver that are usually on the surface of the Earth. To do so, it uses an electronic device called transponder. That's the one that receives, amplifies and resends the signal. And usually a communication satellite has several transponders. There are over 2,000 communication satellites in Earth orbit, and they are used both by private and government organizations for television, broadcasting, for telephone calls relaying, for radio transmission, for internet access, and for other military applications. Some of these applications are, for example, ship-to-shore maritime communications, internet access for remote places like rural classrooms, or vital data and communications for petroleum operations. There are two major classes of communication satellites, passive and active. Passive satellites only redirect the signal coming from the source toward the direction of the receiver, and they do so usually by reflecting this signal. With passive satellites, the reflected signal is not amplified, so when it returns to Earth, it's very weak and it needs very big antennas. Active satellites, on the other hand, amplify the received signal before retransmitting it, and if they are digital, they can even regenerate the complete signal. So the signal that is received on the ground station is much higher. The problem with this kind of satellites is that they need more power, so their active life is shorter. Now we're going to see which communication frequencies are used. For satellite communications, microwave frequencies are used because the propagation characteristics of these bands are suitable for this kind of transmission. There are 4 radio frequency bands used for satellite communications, both civil and military. And the lower the frequencies, we will have less bandwidth and need bigger antennas, because when the frequency is lower, the antenna has to be bigger, but they perform better under adverse weather conditions as rain or snow. The bands going from lower to higher frequencies are called C, X, Ku, and Ka. Now we're going to see a very interesting concept in satellite communication, that are the geostationary satellites. To an observer on the Earth, a satellite in a geostationary orbit appears motionless. It's in a fixed position in the sky. And this is because it revolves around the Earth at the Earth's own angular velocity, that is 360 degrees every 24 hours in an equatorial orbit. You can see it on the corner of the slide on an animated GIF as how the satellite and the Earth are moving at the same time. How do they do that? The satellite has to be located in a circular orbit over the equator that is at 35,786 kilometers, that is 22,236 miles above the Earth equator, and following the direction of the Earth's rotation. This way, it rotates at exactly the same speed as the Earth. A geostationary orbit is useful for communications because ground antennas can be aimed at the satellite without any need for movement. They don't have to track it because the satellite is not going to move. So the receiving stations are quite inexpensive. In applications that require a large number of ground stations, for example, direct TV distributions, the savings in ground receiving equipment can more than outweigh the cost and complexity of placing a satellite into such a high orbit that is very far from the Earth. The concept of geostationary communication satellites was first proposed by Arthur C. Clarke in 1945 in a British magazine, and that's why the term Clarke belt is employed as a description of the geostationary orbit. The footprint, what's called a footprint of a communication satellite, is the ground area that its transponders offer coverage. And together with the transponder power, determines the satellite dish diameters required to receive the signal of each transponder. For the same power, the bigger the footprint, the bigger the antenna on the Earth, because the signal will be spread over a larger area and less power will reach it. There is usually a different map for each transponder or group of transponders, as each may be aimed to cover a different area on the Earth. We're going to move from geostationary satellites to low Earth orbit, LEO, that typically orbit in a circular orbit between 160 and 2,000 kilometers above the Earth's surface. They have a period that is a time to revolve around the Earth of about 90 minutes. Because they are low, these satellites are only visible from within a radius of roughly 1,000 kilometers from the sub-satellite point, and they change their position to the ground quickly, relative to the ground quickly. So even for local applications that only need a small coverage, a large number of satellites is needed if the mission requires uninterrupted connectivity. Other applications, like for example taking photos of the Earth, can tolerate not having a continuous coverage, and you can have photos, for example, every 90 minutes of the same place. Low Earth orbiting satellites, on the other hand, they are less expensive to launch into orbit than geostationary satellites because they are lower, and due to the proximity to the ground, they do not require the same signal strength, because the signal strength in radio frequency falls off as the square of the distance from the source, so being much farther, like in geostationary satellites, has a dramatic effect on the signal strength. And other advantage is that they have less latency. Latency is the time required by the radio wave to reach the satellite and come back, that with satellites that are 35,000 kilometers or 36,000 kilometers from the Earth, it's noticeable, for example, for voice calls. So there is a trade-off between the number of satellites and their costs, and for some applications they can be more cost-effective than geostationary satellites. When it comes to delivering full-time communication service over a given region, LEO, also low Earth orbit, requires very large constellation of small satellites, what can translate into higher cost of deployment and operation. So there is a balance, and depending on the application, geostationary satellites will be better than the low Earth orbit, or the other way around. Now we're going to go to the frequency allocation process, because allocating frequencies to satellite services is a complicated process that requires international coordination and planning. This is carried out under the auspices of the International Telecommunication Union, ITU, and to facilitate this frequency planning, the world is divided into three regions. Region 1, that is Europe and Africa, and what was formerly the Soviet Union and Mongolia. Region 2, that is North and South America and Greenland region, and Region 3, that is Asia, excluding the parts that are included in Region 1, and Australia and the Southwest Pacific. With these regions, frequency bands are allocated to various satellite services, although a given service may be allocated different frequency bands in different regions. Some of the services provided by satellites that have the frequency allocations are, for example, Fixed Satellite Service, or FSS, Broadcasting Satellite Services, or BSS, Mobile Satellite Services, Radio Navigation Satellite Services, Meteorological Satellite Services, or Amateur Satellite Services. We're going to speak now about the receiver. To receive a satellite transmission, any user need a proper receiver. Depending on the distance to the satellite and the transmission power, larger or smaller antennas will be used. For geostationary satellites, the most used antennas are the parabolic one, the parabolic dish, that has to be aimed very precisely to the desired satellite. The ground stations used for two-way satellite communication with small parabolic antennas that are usually around 1 meter are always below 3 meters are called VSAT for very small aperture terminal, and they have data rates usually ranging from 4 kilobytes per second to 4 megabytes per second. There are also satellite-based communications in which the antenna has to track the satellite with mechanical systems in real time. That is sometimes because the ground or sea station is moving, and in other times because they are tracking a constellation of moving satellites of low Earth orbit, for example.